The goal of today is to present the main theory of Galois theory, which classifies completely the intermediate extensions of a certain finite Galois extension. Let me first quickly recall that if we have a field extension L over F, then we can define its Galois group which is denoted by G of L over F as the group of all F automorphisms of L. So these are field automorphisms of L that fix F. For the rest of today, characteristic of all our fields will be fixed to be 0, and this is because I want to use the primitive element theorem. That says that if L over F is a finite field extension and both fields are characteristic 0, then there exists a primitive element gamma in L. It is such an element gamma that L can be obtained from F by adjoining just this one element gamma. So this element is called a primitive element of this field extension. I also want to fix certain terminology. I've already used it, but let's now make it formal. If L over F is a field extension, then the field extension K over F is called an intermediate field extension. If it fits in the tower of field extensions that F is contained in K, and K is a subfield of L. And an intermediate field extension is called proper if K is not equal to neither F nor L. If K is not F and K is not equal to L. Note that if L over K over F is a tower of field extensions, then every K-linear automorphism of L is F-linear. So the Galois group of L over K is naturally a subgroup of the Galois group of L over F. Because if something fixes K, then it also fixes F because F is a smaller field. So, lemma number 1. If L over F is a finite field extension, then the Galois group G is finite. And the order of this group divides the degree of the field extension. Okay, let me prove this. Proof of lemma 1. Note that this group of automorphisms of L, G, fixes F by definition here. So F is contained in the fixed field of G. So it is saying that every element of F is fixed by G. And so we have a tower of field extensions, L over L superscript G over F. Now let us use the multiplicative property of towers and compute the degree of the field extension L over F. It is equal to the product of the degree of L over LG and LG over F. But now recall that we proved a fixed field theorem last time, which said that the degree of the field extension that is obtained as taking a field, as viewing a field as an extension of its fixed subfield by a certain group. This degree is equal to the order of this group. And so the degree of L over F is a product of the order of this group by some natural number. And so we can conclude that G divides the degree L over F, which is exactly what we wanted to prove. In particular, because we started with a finite number, the order of the group must be finite. Okay, so in this lemma, we took the subfield of elements that are fixed by the Galois group of this extension. And sometimes this subfield coincides with the base field. Or it is equivalent to saying that the order of the Galois group is equal to the degree of the extension. This situation has a certain name, and we say that a finite field extension L over F is called a Galois extension. If this situation happens, if the order of the Galois group of L over F coincides with the degree of the field extension, or equivalently, the fixed field of the Galois group coincides with the base field F. Okay, lemma number 2. if G is a finite group of automorphisms of some field L, then the field extension L over the fixed field is a Galois extension, and its Galois group is equal to the finite group that we started with. Proof. So first observe that G is some group of automorphisms of L that fixes LG. And therefore, G is contained in the Galois group. So it is a subgroup of the Galois group. And since it is a subgroup, its order divides the order of the Galois group. But by lemma 1, we have that the order of the Galois group divides the degree of the field extension, which again by the fixed field theorem, as here, is equal to the order of G. And so we know that there are two numbers which divide each other, and therefore they must be equal. And since G inside the Galois group is a subgroup whose order is equal to the ambient group, it means that these groups coincide. And lemma number 3 says that if L over F is a finite field extension and gamma in L is its primitive element, which exists because we assume that characteristic is equal to 0. So L is equal to F adjoin gamma. Then we can take its minimal polynomial. F is the minimal polynomial of gamma over F. And let gamma 1 through gamma R, let this be the set of all roots of F in L. Then I can show the following. So for every index I, there exists a unique F isomorphism sigma sub I that sends gamma to gamma I. These F isomorphism sigma 1 through sigma r. These are all F automorphisms of L. So the Galois group of this field extension as a set is equal to sigma 1 through sigma r. However, we don't know multiplication. We don't know group structure. So if we compose sigma I with sigma j, we don't know what this is in general. It will depend on the field extension. And as a corollary of A and B, we can say that the Galois group of L over F has order R, and R divides the degree of the field extension. So this part is an automatic consequence of this equality of sets, and the divisibility follows from the first lemma that we proved. So let us prove this lemma. L is a field extension obtained from F by adjoining gamma, but gamma I is a root of a polynomial that is irreducible over F. Therefore, we can write that F gamma being isomorphic to F adjoint X not out by F. We can write that F adjoint gamma I is isomorphic to this quotient 2. So in this sequence of isomorphisms, the identification sends gamma to X, and here we send X to gamma I. And so when we take this composition, it will be the F automorphism sigma I that we wanted. And furthermore, because gamma is the only generator of L, and we know how sigma I acts on this generator, it means that sigma I is unique among those that send gamma to gamma I. And so we proved part A. For part B, we note that if some sigma of F adjoint gamma to L is an F isomorphism. So here I wrote L as F adjoint gamma on the left. Then we know that sigma sends a root of F to probably other or maybe the same root of F. Say gamma I. And here like it says a root of F which we call gamma. And therefore by uniqueness in part A we have that sigma is equal to sigma I. And this concludes our proof. And now I'm ready to prove the theorem about characteristic properties of Galois extension. So assume that L over F is a finite extension. G will denote its Galois group. And as in the beginning of the lecture, characteristic of these fields is equal to 0. Then the following conditions are equivalent. So the first condition is that L over F is a Galois extension. The second condition is that F coincides with the fixed field of the Galois group. And the third condition is that L is some splitting field over F. For the proof, I can note that 1 by definition is equivalent to saying that the degree of the field extension is equal to the order of the group. And by the fixed field theorem, the order of the group is equal to the degree of the field extension, which we get by viewing the fixed subfield as a subfield of L. And so we have that the degree of the longest field extension is from L to F is equal to the degree of the field extension L over LG. So it is further equivalent to saying that the degree of LG by multiplicativity is equal to 1, which is precisely saying that F is equal to the fixed field, which is number 2. Okay, so now I want to prove that number 1 and number 3 are equivalent. So 1 is equivalent to saying that the degree L over F is equal to the order of G. But also if I use lemma 3 as follows. If I write L as f adjoin a primitive element gamma, and f will be the minimal polynomial of gamma over f with roots gamma equal to gamma 1, then gamma 2 through gamma r. All roots of f in L. I know that the Galois group of L adjoint gamma over f would then be equal to, would then consist of R elements. But I also know that the degree of f adjoint gamma over f is equal to the degree of gamma over f, which is equal to the degree of f as a polynomial, because we are adjoining one of its roots. And its degree is equal to r from this equality. So we get that f is a polynomial of degree r that has exactly r roots in L, and it is equivalent to saying that L is a splitting field of f. Which is part 3. And this concludes the proof of theorem. As an automatic corollary, we get that every finite field extension L over F is contained in a Galois extension L prime over F. And this is because we can find a splitting field for a polynomial and this is because we know that every finite field extension is contained in some splitting field, and this splitting field L prime would by characteristic property be a Galois extension. And further, corollary number 2, if L over F is a Galois extension and K is an intermediate extension, so we have this tower L over K over F, then L over K is a Galois extension. And its Galois group, L over K, is contained in the Galois group of L over F. The second corollary is also obtained by viewing L as a splitting field. So if L over F is a splitting field, then L over an intermediate extension is also a splitting field. And therefore it is a Galois extension. And now I can sum all of these facts together to get the main theorem of Galois theory. It says that if L over F is a Galois extension with a Galois group G, and as usual characteristic 0, then there is a bijection between subgroups of the Galois group G and intermediate extensions of L over F. So that K fits between L and F. If I denote the forward direction of the bijection by alpha and the opposite direction by beta, then this bijection is established by the following rule. If I take a subgroup H of G, then alpha takes it to the fixed subfield of H, since H is a group of automorphisms of L. And conversely, if K is an intermediate extension, then I can take its Galois group G of L over K, and it will be a subgroup of G by corollary 2. And this bijection reverses inclusions. So if I have two groups, H inside H prime, two subgroups of G, then H gives us a fixed subfield LH, which is bigger than the fixed subfield of H prime, because since H prime is a bigger group, it gives more constraints on being a fixed subfield, and therefore the subfield is smaller. Okay, so basically all the ingredients are already on the board, and all I need is to show that alpha and beta are mutually inverse. So let me compute alpha of beta of K, some intermediate extension. It is alpha of the subgroup G, Galois group of L over K. So it is the fixed subfield of this subgroup. But L over K is a Galois extension. So by corollary number 2, and so by characteristic property number 2, the base field is equal to the fixed field of the Galois group. And so alpha of beta of K is equal to K itself. And so alpha beta is the identity map. And for the opposite order, beta of alpha of a subgroup H, this is equal to beta of the fixed field of H, and beta takes it to the Galois group of L over LH. And so by lemma 2, the Galois group of a field extension of this form, where we have some finite group of automorphisms, it is equal to this group of automorphisms, H. So beta alpha is equal to identity 2. And therefore, alpha and beta are mutually inverse bijections. And we proved the main theorem. As an illustration of this theory, I want to describe the Galois group of the field extension L, which I get from Q by adjoining cube root of 2 and complex cube root of unity, which is the same as adjoining cube root of 2, omega cube root of 2, and omega squared cube root of 2. So I claim that L over Q is a Galois extension, and this is because L is the splitting field for the polynomial f, the minimal polynomial for cube root of 2. F of x is equal to x cubed minus 2, and this is equal to x minus cube root of 2, x minus omega cube root of 2, x minus omega squared cube root of 2. Let me draw these three roots on the complex plane. So two i's and radius I want it to be cube root of 2. And then on this circle, cube root of 2 will be one of the roots. Then omega is a cube root of unity, so it is 2 pi over 3 degrees from 0. Here we have omega cube root of 2. And the third root is here, omega squared cube root of 2. Let me call these roots alpha 0, alpha 1, and alpha 2. Okay, so I know that complex conjugation, which I denote by tau, is in the Galois group of this field. Galois group of L over Q. So tau fixes cube root of 2, but takes any complex number to its conjugate. And so we see that it fixes alpha 0, but it exchanges alpha 1 and alpha 2. And we have another another Q automorphism of L, which sends, let me call it sigma, which sends alpha 0 to alpha 1, and alpha 1 to alpha 2, and alpha 2 to alpha 0. So I have this sort of carousel like this. Sigma, sigma. So you still need to check that sigma is well defined, but for example, you can check that the defining relations of L, so we can represent L as a quotient of some polynomial ring, are satisfied. So that sigma is well defined. And so we have a group that contains this transposition of roots and the long cycle acting on roots. And this group permutes all the roots. So the group of permutation of these roots is S3. And we know that permutation groups are spanned by one transposition and one long cycle. So the Galois group of L over Q at least contains this group S3. But we also know that the degree of this field extension L over Q is equal to 6. And the number of elements in S3 is equal to 6 because it is 3 factorial. And so S3 is therefore the Galois group of L over Q. And I can draw the picture. If I have L, I have 3 field extensions which are obtained by adjoining one of the roots, one of cube roots of 2. And another subfield is Q adjoin cube root of unity. And these are all the intermediate extensions. So the degree of Q alpha naught over Q is 3. Here it is 3, 3. Degree of this extension is 2. Okay. And so when we are looking for subgroups that correspond to each of these intermediate extensions, we want, for example, the order of the subgroup that fixes alpha naught to be equal to 2. And we know that sigma fixes alpha naught. So the group that corresponds to Q adjoin alpha naught is the subgroup of 2 elements consisting of 1 and complex conjugation tau. And for example, we can say that the group that fixes Q is the whole S3. And in this example, we see that it is indeed that smaller subfields correspond to larger subgroups of the Galois group of L over Q.